First concept is self-ionization of water. Are we happy with the idea that water can ionize with itself to form what? Hydroxide and hydronium ions. Happy with that idea? Okay. The idea is also that it's an equilibrium system, and at 25 degrees Celsius, this Kw is what value? 1 times 10 to the negative 14. Somebody asked me if you could just write 10 to the negative 14 without the 1 times. No. So, this is an equilibrium system. If I was to add some HCl into this equilibrium system, which one of those 4 substances would increase in concentration? The hydronium, the H3O+, which would do what to the forward rate of reaction? Increase, decrease? Stay the same, because you haven't done anything to it. What would happen to the reverse rate of reaction? Increase, which would do what to the concentration of OH minus? Decrease the concentration of OH minus. Okay, so it's effectively saying if one goes up, the other one must go down. Okay? These 2 concentrations are linked whenever you're dealing with any solution in water. So as one goes up, the other goes down. Which means that we have a new definition of neutral. Neutral means when they are equal, the concentration of OH minus and the concentration of hydronium ions are equal. What would be our definition of acidic then, using these 2 ion concentrations? Which one will be higher? The hydronium ions will be higher, and the basic would be the hydroxide ions are higher. This is our new definition of acidic, basic, or neutral. And anytime you get asked to say, explain why something is acidic, or explain why something is basic, or explain something like that, you have to state something, and especially if it's in solution, you have to state that it is about the concentration of hydronium and hydroxide ions. Okay? Is this ionization endothermic or exothermic going forward? Who remembers? It's endo going forward and exo going backwards. Okay? So, if I reduce the temperature, what happens to the forward rate of reaction? What? Decrease. What happens to the reverse rate of reaction? Decrease. Which one decreases more? Why? Because it's endo, which means that which one is favored? Happy with that? Reverse is greater? If the reverse... Sorry, yep.
Wait, how do we know what the forward rate of reaction is?
Oh, it just is. Like, it's something you memorize. It's something you memorize or you get told in the question in some way. But you should just memorize that this reaction, the forward is endo. Because this reaction is quite unique and you should kind of memorize quite a bit about it. Okay? All right. So, if I then reduce the temperature, what happens to the concentration of H3O+? Concentration of H3O+ does what if I reduce the temperature? What happens to it? It decreases because I have favored the reverse reaction. Okay? If the concentration of H3O+ decreases, what happens to the pH? Increases. So, does that mean that if I take my water at 25 degrees Celsius, it'll have a pH of 7? If I then decrease the temperature, so now it's water at 20 degrees Celsius, the pH is now 7.3. Is this now a basic solution? No, it is not a basic solution. Why? Because when the reverse rate of reaction is favored, it's also going to consume both the hydronium ions and the hydroxide ions. And they're going to be consumed equally. So therefore, if they are going to be consumed equally, the hydroxide ion concentration also decreases, that means that both of them will be equal still. OH minus concentration will be equal to H3O plus concentration, even though the pH is not at 7. Even though the pH is not at 7. Because they're both going to decrease, but they're going to decrease equally. Right? And so therefore, you're going to have pure water at temperatures outside of 25 degrees Celsius. If it's not pH 7, doesn't matter. Because it's still neutral, because we have a new definition of neutral. New definition of neutral and of acidic, basic, and neutral. Right? So, that is Kw, that is self-ionization of water. All right? pH calculations. pH calculations. Are we happy with the idea of pH calculations? So now we can work out the pH of bases. How do we work out the pH of bases? Remember, pH, what do you need? You need the concentration of hydronium ions. That's what you need to get the pH of something. How do you get the pH of bases considering they don't have a hydronium ion concentration? AJ? Hydronium ions times H ions, what? Okay, so bases are OH minus concentration. And what AJ I think is trying to say is that Kw is equal to H3O plus multiplied by OH minus. That's the equilibrium expression for the self-ionization of water. Right? So you have one of those, and we have the Kw at 25 degrees Celsius, you can solve for the final H3O plus just by rearranging the equation. The H3O plus will be equal to what? How do you rearrange that equation? Because we're good at rearranging stuff. What? Evan? Okay. Take a leap of faith. You can do it. We believe in you. Everyone cheer Evan on. Come on. Rearrange the equation. Okay, we need to get this rearranging equation stuff, yeah? If I said A is equal to B times C, B is equal to? A divided by C. So apply that same thing here. Kw divided by OH ion concentration. Okay? So that's how you get H2O plus from the OH minus. Okay? However, this is not the only types of calculations. What types of calculations should we expect? You should expect things like acid dilutions. You can be expecting acid combinations. You can expect, acid combinations? You can expect acid plus base, limiting reagent, and excess calculations. Right? But it's those three are the major types of calculations that you can expect. Or you can even just do a base calculation. That's how they increase in order of difficulty. Okay, there are all examples on those. Yes, Kate?
Can you find pH by doing 14 pH?
Oh, that's a sucky way to do it. Yes, you can. It's a sucky way to do it. Don't do it. No. Because sometimes you're going to get a negative POH. So what do? You add it. Yeah, but because it's subtracting a minus. But, just don't do it. Just solve for pH. Okay? Just don't do it. It's like drugs. All right? Yes, Archer. What?
Will they ever tell you, give you a question at a different temperature other than 25 and then tell you what the Kw is?
Yeah. So, if you get Kw at a different temperature, you can work out what the pH is at neutral because they'll be equal. So let's have a think about that. Kw is equal to H3O plus and OH minus. If it's neutral, then it will be these two are equal. So if you were to change each of those expressions into an X, you could say that they're both X's. And so therefore you'd be able to say that it's x squared. Right? So if you were given a Kw at a different temperature, if it's x squared, you can work out what x is by what? Square rooting Kw, yeah? Square rooting whatever Kw is at that particular temperature. And then you can use that to work out the pH at a different temperature. That has occasionally turned up in various exams. Okay? But it only generally works at neutral when they are equal. Because if you have two variables, then it's not easy to solve. Okay? So, and you don't really need to solve it because you're just solving for pH anyway at any temperature. Because you just have to have a concentration. Right? Okay. So, that's pH calcs. You really need to know, or at least have practiced a few of each of these. Anyone not understand what I mean by any of those? Base pH calcs, which one, Riley? Okay, so if I say that I have a 50 mils of a 1 molar HCl, and then I add in 250 mils of water, that's a dilution. You feel confident you'd be able to work out the pH of that? Make sense? Yeah? And then a combination is I have 50 mils of 0.4 molar HNO3, and then I add in 20 mils of 0.3 molar HCl. I put those two together, and then mix them up, and then work out what the pH is going to be. Something like that. Okay? There are examples on there, and if you want help, you can find an example and then ask to walk, or try it first, and then ask to be walked through it. Okay? Any other questions? Okay, let's move on. Buffers. What do we know about buffers? Buffers are made up of what? Conjugate somethings. Conjugate bases or acids with oh, no one's watched this video. Everyone's going to be like, yeah, we know everything about buffers by Wednesday when you get tested on it. Weak acids. Do I put the weak acids here? No. You need the weak acid and its conjugate base. Come on. We want to move faster through this, not slower. Okay, so weak acids and conjugate base and a weak base and a conjugate acid will make a buffer. What is a buffer? What is it defined as? A solution that can oppose small changes in pH when an acid or base is added. Okay, so solution that can oppose the small changes in pH when acid or base is added. Right? How does it work? Let's go through what happens. So, if I have a weak acid, let's say it's ethanoic acid, I can have its hydrolysis equation here. What will it form? It's a weak acid, so what's one of the substances it's going to form? Anyone? AJ? Ethanoate ions and hydronium ions. Okay. So, if I have a concentration time graph here, if I have a weak acid by itself, I have this orientation. Okay? Where the CH3COOH is in high concentration and the CH3COO is in low concentration. Why is it in that orientation when it's a weak, if it's just a weak acid? Will? Doesn't fully ionize, you're going to have low volumes of product. So how do I add in more CH3COO minus? Do I go to the cupboard and look for the bottle that says ethanoate ions? Because you can totally find a bottle that just contains ions. What do you have to do? You have to add in its delta? It's salt. So for example, sodium ethanoate could be added to make it have a high enough concentration. Okay, now, so say at this point I add H plus ions by adding an acid in there. Which one of those four things changes its concentration? Which one of those four substances in that equation changes concentration? Hydronium. Go up or down? Up. The hydronium levels go up. Okay? Remember, whenever we're dealing with these acid bases and equilibrium, the hydronium or the hydroxide ions is always the one that changes. So, that went up. What happened to the forward rate of reaction? Stayed the same. What happened to the reverse rate of reaction? Goes up. Which one's favored? What's the net reaction? Reverse rate of reaction is the net. Happy with that? Okay. So, we had a sudden spike because you added that. A net reverse rate of reaction means the yellow line goes up or down after the spike. Up or down after the spike? Down. Okay, so let's go that way. Happy with that? What about the blue line? Does it go up or down? Down. What about the red line? Up. Happy with that idea? Okay. I add more H plus over here. Does the exact same thing. Okay, does the exact same thing. The point is that at this point here and this point here, even though I've added acid, the pH hasn't changed much. Why hasn't the pH changed much? Because why hasn't the pH changed much? Because pH is dependent on hydronium ions. Has the hydronium ions changed much? Not really. Not as much as it would have, considering it actually, you added that much and you added that much, but only it went up by that much, which is not a lot, comparatively. Yeah? So, this continues. If you continue to add H+, you continue to add H+, this is going to go up and down, up and down, up and down, until there is a point where it can happen no longer. Who can see why it might no longer be able to occur? Archer? When the blue hits zero. At some point, blue's going to hit zero. Okay? When blue hits zero, there's nothing for the hydronium ions to react with anymore. So once it hits zero and then I add some more, what happens to it? Stays the same. I add some more, stays the same. Add some more, it stays the same. So there is now a massive jump in pH. Okay? As opposed to the very small jump in pH when I had the buffer present. Right? So, when you run out of one of those two ions, you will lose the ability to buffer. How much you can add is known as the buffering what? Capacity. The ability to buffer how much acid or base is the buffering capacity. It's dependent on the concentration of those two, weak acid and its conjugate base, or weak base and its conjugate acid. Right? This is all opposite if you add in OH minus instead. Happy with the addition of OH minus instead of the addition of H plus and everything being opposite? Okay? Right? Because then we will move on to say, how do you make a buffer? How do you make a buffer? How to make? You drink lots of protein and then you go to the gym lots, then you become buffer. Mr. Lim's so funny. Okay, what else? See, Mr. Farley was buffer. I bet if you splashed acid at him, nothing would happen. Anyway, so, how do you make a buffer? What do you need to do? You need to add in a salt of? Good. A neutral ion and a conjugate, let's just say base of a weak acid. And what else? Because that's one half of it. You've put in the conjugate base, now you need to put in the weak acid. So you need a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. You put those two things together and you want it in equimolar amounts, and you want it to be at high concentration. What does it mean by equimolar? Equal number of moles. Okay, so looking back up here, this is roughly equimolar, but if you were to have them not at equimolar, it'd be good at buffering one way, but not be good at buffering the other way, because one would run out much faster. Okay, yes, Archer?
Is that how indicators work?
No, that is not how indicators work. Yeah, no. So, we'll go through indicators in a moment. Yeah, okay. So, equimolar and high concentration. If you don't happen to have the salt of the weak acid, can you still make a buffer? Yeah, yes you can. Okay, say this is your weak acid, and by itself, in its weak acid, you have just its conjugate base. All you want is those two concentrations to be roughly equal. So you've got to increase one and decrease the other. How do you increase the concentration of the conjugate base? Yep. Not change the temperature? Tilta? Add what? Add base. A strong base. And only a small amount of strong base. If you add a small amount of strong base, this goes down, this goes up. This goes up. This goes down. Right? You do it again. Right? This goes up. This goes down. And now they are roughly equimolar. They are roughly equimolar. Right? If they're roughly equimolar, then they become a buffer. And if you started off at a super high concentration with the weak acid, then you can bring the concentration down a little bit so that it's still at a high concentration, considering you started at a super high concentration. Right? But the idea is that you can do that as well. Right? That's how you make buffers. Two ways. You add in the salt and the weak acid, or you start in the weak acid and you add a little bit of base, or you start off with the base and you add a little bit of acid. Strong acids. Okay? Next. Indicators. What are indicators? What are they? Weak acids. And their weak acid and conjugate base forms have different colors. Good. Okay, so they're weak things. So this is the weak acid. We're going to call it Hua. Why do you think I've called it Hua? Yeah, because it has to have a hydrogen in it. Although I realize now that if I write Hua, it doesn't make any sense when I do the other part, where it's weak acid minus. Okay? But this is its conjugate base for all intents and purposes. Alright? Okay. So, here's my Hua, and it's red in one form and blue in the other form. If I add acid to it, what's going to happen? Which one of those four things is going to be affected? Which one of the four is going to be affected? The hydronium. It's always the hydronium or the hydroxide. Okay? So what happens to the forward rate of reaction? Stays the same. Reverse rate of reaction. And therefore, what's the net rate of reaction? Net reverse. And therefore, am I going to get more or less of the Hua? More Hua and less conjugate base. Right? Make sense? Right? If I end up with more of the red and less blue, it's going to turn at some point from blue to red. What happens if it was already red? Then it stays red. It just becomes more red even, maybe. Rarely does it become more red. It does not become more red. Don't say that. Right? So, it just stays red if you add more acid and it was already red. Okay? So, for all intents and purposes, it's exactly like all of the other equilibrium systems, except now we have two different colored substances there, and they'll change color when you add acids, bases on there, exactly the same as we did before. Now remember, this is an equilibrium acid-base test. So all of this stuff here